Okay, any questions on the hospitals rule? $25. X cubed e to the negative x squared. Limit x goes to infinity. X cubed times e to the negative x squared. Yes? Okay, so what we have here is a form that x cubed goes to infinity times e to the negative infinity. What is that? Right, because this negative is outside, you square first. So infinity squared is infinity. E to the negative infinity. That's the same as saying, what does the exponential function do as you go out the left side, as you go to negative infinity? So e to the x looks like this. I just did this in my 1414 class today. That's e to the x right there. What happens is you head to negative infinity. Where is it going? Approaches 0. You have infinity times 0. Augustine? I've just put this in today. Yeah. Are y'all okay with that? Oh, shit. What the heck? There we go. So now that's one way to look at it. If I were doing this problem, I probably would have rewritten it and just dropped the e to the negative x squared down to the bottom as an e to the positive x squared, just using properties of exponents. Right? Negative power means you can drop it down. And now you would have the form infinity over infinity. Is that what you tried, whoever's asking me about this? Or, and now you can use L'Hopital. So by L'Hopital's rule, x goes to infinity. Derivative of the top is 3x squared. Derivative of the bottom, well, derivative of e to anything is itself, times the derivative of what's there, 2x. Now, before I do anything else, I'm going to simplify this. I get one of those x's to cancel, right? I get 1x, this is x squared, this is x right here. I get one of them to cancel. So I could put something like 3x over, what do you say, 2 e to the x squared. 1x canceled there. And now I have infinity over infinity still. So I take L'Hopital one more time. Derivative of top is 3. Derivative of the bottom is 2e to the x squared. So itself again, then times 2x. And I think at this point we're done because the top is fixed. It's at 3 and the bottom's going to infinity. A fixed number over something that gets very large goes to what? 0. $29. X is going to approach 0 from the right. One over x minus 1 over e to the x minus 1. So let x go to 0 right now. What happens when you have a fixed positive number, 1, divided by a very, very small positive number? Infinity. Becomes infinite. minus, okay, e to the 0 is 1. 1 minus 1 is 0. So again, you have a fixed positive number divided by a very, very small positive number, which is going to be infinity again. So infinity. Infinity minus infinity is one of our indeterminate forms, right? And so what can we try here? Try and turn it into a product or a quotient, whatever. I see two denominators, so my instinct is to want to put these together as one fraction. Let's just see what would happen. I would have to get a common denominator. This might not work, but I'm just going to try it. E to the x minus 1 over x e to the x minus 1. So what I did here is I introduced an x over x here, and e to the x minus 1 over e to the x minus 1 here. So I get a common denominator. Y'all with me? Yes? Minus x, yes, thank you. Sorry. My fault. Forgot to multiply the x. So this times 1 is this, minus 1 times x is x. Denominator here. Now let's just check it. It should be a bad thing. So let's see. 0. E to the 0 is 1. 1 minus 1 is 0. Then replacing this with 0, I get 0 on top. And on the bottom, I get 0 again. But now I can use L'Hopital's rule. Not too excited about it. Just kidding, I am excited. So we go derivative of the top. What is the derivative of the top? E to the x minus 1. That's it, right? Derivative of e to the x is itself. Derivative of negative 1 is 0. Derivative of negative x is negative 1. Here, what am I going to have to do? Product rule. Or I could multiply this out and then do that derivative. It doesn't matter. Do you have a preference? Just go straight to product here. Okay, straight to product rule right there. Derivative of the first one is 1 times this, plus, now the derivative of e to the x minus 1, just e to the x times the first one, x. So it's just x e to the x. You with me? Check it. X goes to 0. E to the 0 is 1. 1 minus 1 is 0. So I have 0 on top. E to the 0 is 1. 1 minus 1 is 0. 0 times e to the 0 is 1. So 0 times 1, that's going to still be 0. So we get 0 over 0 still. Uh-oh. Okay, L'Hopital again. L'Hopital. Derivative of top, e to the x. Derivative of the bottom. So derivative e to the x is itself. Minus 1, derivative of negative 1 is 0. But then here, what do I have to do? Product rule right there. So I'd have plus, what's the derivative of the first one? 1 times e to the x, so e to the x, and then plus derivative of this times this, so e to the x times x. Just going to write x e to the x. Ugh. We getting anywhere here? You could cancel one out. Let's just try plugging in right now. What happens? E to the 0 up here is what? 1 over e to the 0, 1, e to the 0, 1, 0 times e to the 0, 0. So 1 plus 1? So 2. 1/2? That help? Did you try something else, or is this what you went for? Okay. So the common denominator is kind of, you either want to try and turn it into a product, or if they're two fractions, put them together. Any others? Which one? 23. Okay. X is going to 0. We have cotangent 2x sine 6x. Now, because you may not know what cotangent is doing, it might be best to rewrite cotangent in terms of sine and cosine. What is cotangent in terms of sine and cosine? It's cosine of 2x over sine of 2x. But then you had sitting next to that the sine 6x. That might help to see what's happening. X goes to 0. Plug 0 in here. Cosine of 0 is 1. Sine of 0 is 0. So we have 0 on top. And then, of course, on the bottom, sine of 0 again is 0. So we get 0, 0. That's not good. Limit. L'Hopital, then limit. All right, so I have to do a product rule on top, don't I? Derivative of cosine of 2x is negative 2 sine 2x. So I already did the derivative. Cosine is negative sine of 2x, then times the derivative of what's inside, which is 2, and then I pulled that 2 out front. Then times the second function, plus, now derivative of sine of 6x is 6 cosine 6x times the first one, cosine 2x, over derivative bottom, 2 cosine 2x. Okay. It's going to work out good. X goes to 0. Sine of 0, 0. Sine of 0, 0. This is all 0. Cosine of 0, 1, but then times 6, right? So that's a 6. Cosine of 0, 1. So this is going to be 6 times 1 times 1. So 6 on top. And on the bottom, 2. The answer is 3. Is that all right? Questions? 24. Limit x goes to infinity. I'm going to rewrite it first. Square root of x over e to the negative x over 2. Oh, sorry, I moved it down already. Do you agree that this is the same thing? That's the same as this. Negative x over 2 means I can drop it to the bottom, make it e to the positive x over 2, but I just rewrote x over 2 as 1/2 x. We okay with that? Let x go to infinity. What form do we have here? On top? It's going to infinity, though, right? So square root of infinity is infinity over what's e to the infinity? Infinity. So we have the appropriate form for L'Hopital. Limit x goes to infinity. Derivative of the top, 1 over 2 root x. Derivative of the bottom is itself times what? 1/2. Good, the derivative, what's there? All right, this is a critical juncture of the problem. Juncture? What does this go to right here as x goes to infinity? That goes to 0. Over, what does e to the infinity go to? Infinity. Is 0 over infinity a bad thing? The top is wanting to get small, right? The bottom is wanting to get big. They actually help each other out, right? When you have a fixed number, like if you had 1 over infinity, that goes to 0, right? Because the top is just staying there, the bottom's getting bigger. What if I told you not only is the bottom getting big, but this one is also trying to get small too? So imagine taking like 1/2 over infinity. That's still going to get small. Then I do 1/4 over infinity. Does that make sense? It's just helping get there faster. So the answer here is 0. Okay, I'm going to do one more example, but it's going to be from last class. We got stuck on this problem right here. Remember this? I was trying to find the limit as x goes to 0 of sine x to the x. We said it was 0 to the 0. Does this ring a bell? And so what we did is we said, whenever we have 0 to 0, we rewrite the limit, we call it y, and then we did the natural log on both sides. That way we could pull that power out. Yes? And we were at this stage right here, where we had pulled the power out, and we were looking at it. We said, okay, this is 0 times infinity, basically. And so I need to, whenever we have this, we can take one of these and drop them down, and I dropped the x down as a 1 over x. Yes? Then we did L'Hopital's rule. I did the derivative of the top, and the derivative of the top is actually 1 over sine x times the derivative of what's inside the natural log, so cosine x. But instead of writing this down, I wrote cotangent x. And then we did derivative of the bottom, which was this. And at that point, we tried to do L'Hopital again. And we got kind of hung up, and it started getting really ugly, right? So I want to take us back just to this step right here. I'm going to rewrite this just like this. All right, actually, I'll copy it. And let me bring it to today's stuff. I'm sorry? I didn't what? I didn't? The video? The notes? Oh, I didn't? Okay, I'll upload them. You sure? Yeah. Last class was day 17. Okay, it was there, but I didn't upload it. Well, I don't know. No, maybe I didn't upload it. I'm about to check. I was logged in, so I may as well. Day 17. That's weird. 16 and 17 weren't there. Did we have a 16? We did. Well, they're there now. Thank you for letting me know. Okay, so here's where we were, right? Let's go ahead and do natural log y. That's the left side. Haven't touched it. I am applying L'Hopital's rule right now. But I'm going to leave the top as cosine x over sine x. And then on the bottom, when we took the derivative, we got negative 1 over x squared. Yeah? We good or not? Yes? Okay, now, watch what I do now. I'm going to take this fraction, I'm going to flip it up. Like division is the same as multiplication, the reciprocal. So I have natural log y equals, no L'Hopital, I'm just rewriting now. Negative x squared cosine x over sine x. So I brought this up, flipped it, and when I flipped it, I had x squared on top and a negative 1 on the bottom. The x squared times the cosine x is this. Then the negative doesn't matter where it is. It can be on the bottom or it can be on the top, so I just put it on the top. That all right? Just algebra flipping? Okay, now check this out. See if you recall this. I'm going to put the negative out here as a -1 so it doesn't get in our way. Tell me if you believe this is the same expression. Is that the same expression? Negative is out here. X squared I could write as x times x, right? And then cosine x, I can just put it to the side. So that's the same thing? Why would I want to do that? Yeah, what is this right here? That's going to go to 1. Remember, that was one of the ones we had that quiz. I said, know these two limits. And I said it worked both ways. You could have sine junk over junk, or it could be the junk over sine junk. That'll go to 1 as long as the junk matched and as long as the junk was going to 0, which in this case it is. So if I take my limit right now, this goes to -1, this goes to 1, this goes to 0, and cosine of 0 goes to 1. And all that multiplied together is just 0. You could have also just done L'Hopital on just this piece. L'Hopital, 0 over 0. You get 1 over cosine x, and then that's also 1. So in any event, we are at this point, natural log y equals 0. And we are trying to figure out what y is, not natural log y. So we have to do what on both sides here? E, right? So e to the natural log y equals e to the 0. What's e to the 0? 1. So our answer was 1. The limit is 1. I just didn't want to leave that undone. So it's resolved now. You see how just leaving it as cosine x over sine x versus when we switched it to cotangent made all the difference in the world there. All right, let's move on. We have big things to do today. We are starting chapter 4, where we're going to do applications of differentiation. We've actually, oh, the bonus, yeah. You have that bonus? I'll take it. I'll come get yours so you don't have to roll over here. Anyone else? Thank you. All right, so we have done some applications of derivatives, namely the related rate problems, right? Those word problems. A cone is growing so that, whatever the plane's flying overhead, that was application. But now we're going to get into some different applications. So this entire chapter is dedicated to applications of differentiation. One of the main goals of this class was to be able to figure out what the maximum and minimum values of a function are. And so we have some definitions and then some pictures, and we'll just go through this and I'll show you. We'll get to this thing called the closed interval method. So definition, the absolute maximum and minimum values. So if you're given a function, right, it's defined on some domain D, and there's some number C in the domain. So you have maybe the part of the number line or the whole number line, and somewhere on the number line is the value C. F of C, that means the function's value at that point, is called the absolute maximum value of the function f on the domain D if f of c is greater than or equal to f of x for all x in the domain. What does that mean? It just means that at that point, you are at the highest point on the entire graph. That value, right, the value of your function there, is bigger than all other values of the function for all other x's that you could possibly come up with in the domain. On the other hand, you'll call it the absolute minimum if it is less than or below every other point on the graph, then it would be the absolute minimum. So we're just talking about the highest and lowest points on a graph. That's it. In either case, f of c is called the global max or min. They're sometimes also called the extreme values of f. So you'll hear that in different authors and different books. Different tutors will say different things. Global max, global min is the same as extreme values, or extreme max, extreme min, or absolute max, absolute min. Those are all interchangeable. Yes? These are the y values, yes, because it's f of c, that's the function's value at the function, it's the y value. All right, now let's compare that to what's called a local maximum or minimum, right? Given a curve f defined on some domain D and then some point inside the domain again, the y value of that function is called a local maximum of f on D if it is bigger than every other point, but not on the entire domain, for all x near C. Near C. What does near mean? All right, I mean, it's relative, right? We talked about that in the very beginning of class. Remember, what was, am I close to you? Remember that? And then we're talking about, am I close to you? Am I close to SeaWorld? Am I close to the sun? Remember me saying that? Okay, near is very vague. So let me give you an idea. If we all stood up, right, we would have a, and we looked at heights, right? We would have in this classroom a local maximum, a tallest person. They'd be the tallest person in this room. Are they the tallest person on the planet? No. Locally, they're the max. Globally, they are not necessarily the max. Does that make sense? Same with the minimum. We could, shortest person, we could say, okay, you are the local minimum. Globally, you're not the minimum. So the difference is we search the entire domain for the highest and lowest, or we search just locally for the highest and lowest. So here's a visualization. So take a look at this function. I have this function defined on a closed interval, meaning it starts here and it ends here, right? It doesn't go, there's not like arrows representing the function keeps going in that direction forever, right? These 2 points are what? These are 2 endpoints, right? Okay, let's look at the local extremes, the local extreme values. This right here is a local, what? Minimum. It's the lowest point near it, right? Look around it, it's the lowest point. This point is also a local minimum. This one is a local maximum. And we could even consider this to be a local maximum because it is the highest point near it, right? And this one right here we could look at as being a local maximum also. Compare that to the globals. This is your global maximum. If you look at the entire function on the entire domain, that's the highest point, right? There's no other higher point. This one is the global minimum, lowest point on the graph. See the difference? Look at this one. Locals, local min, local max, local min. Local max, if you wanted to, you could say that local max here. Look at the globals, though. Ah, a global max was an endpoint, wasn't it? And the global min is not an endpoint. So in this one, our globals happened inside, didn't they? Global max and min were inside the function, inside the domain. This one, I had a global max that was actually at the edge, and a global minimum that wasn't. Yes? You can have more than one, yes. Now, it could turn out that your global max and your global min turn out to be the same value, and that would be if you had a flat line. The highest point on the graph is the lowest point on the graph, is the only point on the graph, the y value. That could happen, but other than that, if it's a nice continuous function, you should have one global max, one global min, as long as it's a well-behaved function. continuous and differentiable. All right, so how about this one? Notice I don't have endpoints, which means that I'm saying that this curve just keeps going forever up and keeps going forever up. So let's look at local stuff. Local min, local max, local min, yes? How about global? What am I going to have global-wise? Am I going to have a global minimum? Right there? Global max? There is none. You can't say there's a highest point on the graph because this keeps going, right? So as soon as you think you're there, there's a point higher than it. So it's possible to not have a global max if your interval goes forever. It could happen that way. We good? Or min? You wouldn't say infinity, no. You would just say no global max. Okay, how about this one? Locally, you would say what? Maybe a local max, local max, local max, local min, local min. Yeah, well, you can have more than one local max, but what about global? What is your global going to be here? Let me show locals. Local min, local max, local min. Local max, local max. It is the highest point next to it, right? There's nothing out the side, so, but look at your global. Why didn't, oh, there they go. Okay. So, you look at your global max. Your global max is actually, the value of the function is 225. So up here, 225, that's how high those points are. But it's happening at two different points, right? Your global maximum is the y value, 255, or 225. But it could occur at more than one place. That make sense? As long as the height's the same. If one of those is a little higher, then it's the global max. And same with the global minimum. We have the same global minimum, the same lowest point, negative 64 is the value. I know it's hard to see that. But it's happening at two different places. Okay? All right, extreme value theorem. Extremely important theorem. All right? If f is continuous on a closed interval AB, what does it mean to be continuous? You draw it without picking up your pencil, right? That's what it means in this class pretty much. Let's say that I have a function that I have to start. Let me see, is this today? Yes. I have a function. It's on a closed interval, AB. That means that at A it's defined and at B it's defined. And I have to connect these together with a continuous line or curve without picking up my pencil. Right? That's the situation. What does this theorem say? If you have that situation of a continuous function on a closed curve, then f attains both an absolute or global maximum and a global minimum in the interval, AB. Which means that no matter how you draw it, you have to have a global max and a global min. Has to happen. You might have it happen at more than one place, but you're guaranteed the existence of a global max and min. Right? Has to be continuous, though, on a closed interval for that to be the case. So what did I have here? So check out this right here. So I just connected these 2 points with a continuous curve. That's my global max. That's my global min, right? Guaranteed they would be there. Let me do it with a different curve. Here's a different curve. Take the other one out of there. Guaranteed, that's a continuous curve, right? I'm going to have a global max and min. There's my global min. There's my global max. Let's do another one. Straight line. Global min, global max. Yeah? Do another one. Vertical asymptote. Global min, global max? Why not? I thought the theorem said we'd have one. It's not continuous. does not apply. This is not a continuous function. So it has to be continuous for us to be able to guarantee that existence of a global max and min. So be careful. That's all that's about. Just be careful. Okay, Fermat's theorem. Let me blow this up so we can see it. This is all in your book, all right? And all these notes are online, of course. If f has a local maximum or minimum, if it does, okay, at some point C, and the derivative exists, then the derivative is 0. Okay. If your function has a local maximum or minimum, locally, local, at some point, and the derivative exists, that's key, then the derivative has to be 0. Guaranteed. That's what the theorem's saying. This theorem is important because it states that our function has a local maximum and therefore derivative exists, the derivative must be equal to 0 there. What this theorem does not say, okay, you have to be careful. The theorem does not say that if your derivative is 0, you're at a local max or min. That's not what it says. It's the order in which things are stated. Let me give you an example that might make a little more sense. If I say this, right? If you are from Texas, then you are from the United States. Yes? If you live in Texas, you live in the United States. Okay. Does it work the other way around? If you're from the United States, do you live in Texas? No. That's exactly what you need to make sense out of this. It says, if you have a local maximum or minimum and the derivative exists, then it has to be 0. It does not say if the derivative is 0, then you have a local max or min. Totally different concepts. Do you understand that? Okay, so here is a visualization where I have a curve. Here's a local max, right? Here's a local max. Here's a local max. So this function has a local max, doesn't it? Since it has a local max, and I go to this point and I take the derivative exists. Why does the derivative exist on this curve right here? Why does it exist here? Tell me. Well, forget that it's 0. How do you know that the derivative exists at this curve? What's not happening there? What do you not have? What are the things that cause problems with derivatives on functions? Jumps. There's no jump here. There's no cusp or corner, right? On this graph, it's continuous, but you can have a cusp and be continuous still, right? You can draw a corner. So I have a local max. I know there's not a cusp, a corner, or a jump. So the derivative must exist there. Therefore, it had to be 0. Same thing here. I have a local minimum. It's a nice curve, right? No jumps, no corners. Therefore, I can guarantee you the derivative is going to be 0 there. Now an example for which it fails. Classic example. Is this a continuous function? Continuous, yes. Is this a local maximum? Yes. The theorem says that if you have a local maximum and the derivative exists, it has to be 0. Does the derivative exist? No. And the derivative isn't 0 there. The derivative is undefined. So it is possible to have an undefined derivative and still be at a local max. So it's a little tricky in the way things are happening here, but you have to pay attention to the logic of things. Is this a continuous function? Does the derivative exist here? Yes. Is the derivative 0? Yes. Is it a local max? No. So wait a minute. The derivative exists and the derivative is 0 and it's not a local max? The theorem didn't say that's what we would get, right? The theorem said if you have a local max or min and the derivative exists, then it must be 0. It does not say if the derivative is 0 that it has to be a local max. It's so important. It's the U.S. citizen means you're from Texas. That's what we're trying to say here. It's a U.S. citizen from Texas. That's not guaranteed. I hope that makes sense. Okay. But there's still going to be a way, all right? So before we can move on, we need to define what are called critical numbers. And they are critical for us to be able to do what we're about to do. A critical number of a function is a number or any number, C, in the domain of the function such that either of these two things are true. Either the derivative at that point is 0 or the derivative does not exist at that point. So if you have a curve and you're finding places where the slope of the tangent line is 0 or where the slope of the tangent line doesn't exist, then wherever that happens is called the critical number of the function. You must be looking at a number that's in the domain, okay? If the number's not in the domain of the function, you can't even talk about it being a critical number. So what's a critical number? It has to be in domain. The derivative has to be equal to 0, or the derivative doesn't exist there, right? That's what it means to be a critical number. Because what we're going to be asked to do is we're going to be told, find the critical numbers of a function. So what are you going to do? Figure out where the derivative is 0 and where it doesn't exist or where it's undefined, which means you're going to have to find the derivative, set it equal to 0. You have to find the derivative, figure out where it doesn't exist. Now, Fermat's theorem again. So this is that same theorem, just kind of restated. If f has a local maximum or minimum at a point C, then C is a critical number of f. It's the same theorem, just restated in a different manner, now using this new definition of critical numbers. So here's what Fermat's theorem says. It says that if you're looking at a local max, I promise you the derivative is either 0 there or it doesn't exist. That's what it's saying. So let's go back to these pictures. Right here, Fermat's theorem. Do we have a local max or min? No, we can't even talk about that then. How about this one? Do we have a local max or min? Yes? Fermat's theorem guarantees us that either the derivative is 0 or the derivative doesn't exist there. Is the derivative 0? Does the derivative not exist? Yes. That's what the theorem is saying. Here, we have a local max here. Does the derivative exist there? Yes. It's 0, right? It's 0. Okay, all of that leads us to what is called the closed interval method. This is the method that you use, that you grab your calculus toolbox, right? This is the toolbox that has all your calculus shit in it, right? And this is one of those things that when you're in a different calculus class, you're like, where the hell is that closed interval method thing? All right? This is a big time deal. All right? I wanted to show you an example to illustrate the importance of this. This is a calculus 3 problem. All right? So what we have is a surface. All right? So imagine this 3-dimensional surface, right? And what we're going to do is we're going to imagine looking at that surface. Here's my surface over here, okay? That's just part of it, all right? And imagine looking down on the ground here, okay? See the ground's right here? Let's imagine that that's the ground. And all I want to do is take just these points on the ground and plug just those points into this surface. If I do that, I get just that piece. Now, what I'll do is I'll take the surface out now so you can see that that green piece is just the part of the surface that lies directly above that region. That make any sense to you? Yes? What we want to know in a calculus problem, in this calculus class, is where are the highest and lowest points on this piece. Where are the highest and lowest points occurring? Understand? Just, I mean, you don't have to understand how to do it. You understand what we're trying to do? Okay, to do this problem, we have to break it into different parts. We look first along this line, and we try and find the highest point on this line. Then we look along this curve right here, which is the backside. Let me take the region out of there. Just this backside, like this. We try and find the highest point on that. Then we go along this third line, which is this red one, and we try and find the highest point there. Each one of those three problems turns out to be finding the maximum or minimum values of a function on a closed interval. That's what it turns out to be, each one of those individual pieces. Finding the maximum and minimum values of a function on a closed interval is exactly what today is about. How to find the absolute maximum minimum value of a function on a closed interval. Regardless of where it comes from, if you have a function of x and it's on a closed interval, this is the way we find the biggest and lowest values of the function. Okay? Now, what if it's not a closed interval? We have a totally different method, and that comes later. All right? This is the closed interval method. And this is actually the preferred way. If you can get something down to a closed interval, things become real nice. All right? Let's look at the method. To find the absolute maximum and minimum values of a continuous function, it has to be a continuous function. Because if it's not continuous, Fermat's theorem doesn't hold, and so you don't have anything. So you've got to have a continuous function on a closed interval AB. First thing you're going to do, find the critical numbers of f. How do you find the critical numbers of a function? Take the derivative, set it equal to 0. Take the derivative, figure out where it doesn't exist. Once you've done that and you figured out where that happens, you want to evaluate your function, your original function, at those critical numbers. You plug in those answers into the original function. So you take the derivative, solve that, take those answers, plug them back into the original function. You plug them back into the what? Original function. No, you won't, because the derivative is where it came from. Okay? So let's try and understand what we're doing. On a picture like this, if I'm trying to find the highest and lowest values here, I realize this is not a closed interval, but let's just say it was. If I want to know what's happening, I find out where the derivative is 0, right? And that would occur like right here, wouldn't it? At this x value, I take that value, I plug it into the function, and that'll tell me how high I was there, won't it? Then I figure out where this is happening. I take that value, I plug it into the function, and that'll tell me how low it was. Is that enough, though, just to look at where that's happening? Is it enough? Is it enough to just look at the inside, or should we possibly look somewhere else? Where? The ends. Couldn't it happen at the ends? Look at this example here. I have a lowest, I have a highest, but they don't happen inside where the derivative is 0, do they? They happen at the endpoints. So the last part of this method is after you've done this and evaluated the function, then just go to the endpoints of the function and see where the value of the function is there. Last thing is just compare all those answers. The biggest value you get out is your global max. The lowest you get out is your global min, and you're done. Understand kind of theoretically what we're going to do? So let's do it. That has to be given to you in the problem. And in a word problem, which we'll get to, it will be implied somehow. All right, so let's do an example. It's fun, huh? Find global max and min values of f of x equals x times 12 minus 2x squared on the interval 0, 6. God, this is going to be fun. This is gonna, I think you're going to like this. Did someone just leave? Yeah? Okay. Try that. Mix. Find the global mix. Some house music in here or something. All right, global max and min values of this function. All right, so the first thing I'm going to look at is the function itself. What I need for this to work is I need this to be what? Continuous. Is it? Why? Because it just looks good. What type of function is that? Almost quadratic. If I squared this, it would be quadratic, right? And then I multiply everything else through by x. It would be x cubed something. That's a polynomial function, right? Are polynomial functions continuous? Back in 1.5. There it is. Theorem 1.59. All polynomial functions are continuous on the entire number line. So since we're here, all rational functions are continuous on their implied domains. All trig functions are continuous on their implied domains. All exponential and log functions are continuous on their implied domains. So we'll keep that in mind as we proceed. So I have a polynomial. This is a poly. So f is continuous. In fact, it's continuous everywhere. I only need it to be continuous on 0, 6. Also, I'm looking. I have a closed interval, don't I? Let me turn my phone off. That means I can use the closed interval method. What? Okay, so let's do this. I'm sorry, I shouldn't have put first step. No, it's not actually. No. 2 Halloweens ago. All right, so first thing I'm going to do, I'm going to let everyone know what I'm doing. I'm going to use what note was that? 4.1.11, which we will call the closed interval method. First step, I need to figure out where the derivative is 0 and where it's undefined. So I want to know where the derivative equals 0, and I also want to know where the derivative does not exist. All right, so first thing, let's find the derivative. So let me write down f of x here. I kind of want to take the derivative and use product rule and some chain rule, but I also kind of would just want to multiply this all out before I take the derivative. You don't want to multiply it out? Okay, what's 12 minus 2x squared? Like 144 minus you would have to expand this properly, right? 12 minus 2x times 12 minus 2x and FOIL it out, right? If you did that, you should get this. Yay? Yes. And then I'm going to distribute an x through, and I think I'll put it in descending order. Okay? Questions? I've done no calculus yet, right? Here comes the calculus, derivative time. So the derivative of this is 12x squared minus, what is that? 96x plus 144. We all agree? Okay, now let me go look at the two things. Where was the derivative equal to 0? Well, that means I have to set 12x squared minus 96x plus 144 equal to 0. It's times like this where I think back on, what math is about. Like, there's probably a class that you took at some point in time where the main goal of like 3 lectures was for you to be able to solve something like that, right? Now it's just an intermediate problem on a test now. I mean, within a bigger problem, right? So math builds on itself. So whenever there's holes in your math, it makes things very difficult, right? This is just a quadratic where you have to do, yeah. I would assume everyone here could solve a quadratic. So, but let's go through this. Any ideas here? Take a 12 out, factor 12 out. I'll be left with x squared what? X squared minus 8x plus 12. Does that factor? X squared minus 8x? You hope, right? Me too, I hope so. What is it? Minus 6 minus 2 equals 0. Agreed? So you get, what are your solutions, and how many of them do you have? Careful. This right here does not factor into our answers because it's just 12, not 12x, right? Divide both sides by 12, it's gone. It's a quadratic. We should only have 2 answers. The 2 answers are what? 6 and 2. Okay, 6 and 2. These are critical numbers. That's a little pound sign, pound hashtag, whatever. Number sign. Critical numbers. 6 and 2. Are those the only ones? Well, I have to look at something else, right? What's the other thing I'm supposed to look at? Where the derivative does not exist. So let's take a look at this derivative. The derivative is a polynomial function, isn't it? It's a quadratic, but it's a polynomial. Polynomial functions are well-behaved functions. They're continuous functions. There's no problems as far as me trying to plug an x in there and having any issues, right? I'm never going to get division by 0. I'm never going to get a square root of a negative number. No problems. No matter what I plug in, the derivative should exist. We should have something, right? So therefore, I'll put NA. Not applicable. Doesn't apply to this problem since f prime is a polynomial function. Now, what would cause a problem would be something like, let's just say our derivative was like something like this, 1 over 2 root x. Let's say that was our derivative. Then we would have to worry about x being 0, right, or x being negative. So we would have to throw certain things out, wouldn't we? Or we would have to address those. But that's not what's happening here. Okay, so I have done the first step. I have found the critical numbers of f. Any questions? Step 2. Oh, no, I haven't finished it. What was step 1? Sorry. What am I supposed to do once I find the critical numbers? Find the critical numbers of f and evaluate f at those critical numbers. So I'm going to evaluate what at these numbers? The original function, right? The original function. Now I'm going to keep saying that, the original function, the original function, the original function, over and over and over, because this is the closed interval method, right? After we're done with this, on another class period, we're going to do like an open interval method. And when you do the open interval method, you get points, but you don't plug them into the original function, you plug them into the derivative, and they're test points, and people confuse the two methods. So closed interval method, your critical numbers go into your original function. So what I need now is f of 2 and f of 6, right? Plug those two numbers in the original function. Now I think I'll go back to the original form of the function. Wasn't it x times 12 minus 2x squared? So I'm going to go 2 times 12 minus 2 times 2 squared, which is 12 times 12 minus 4 squared, which is 12, what's that, 8 squared? What's 12 times 64? What is it? 128? That doesn't seem right. No. Yeah, 12 times 64. 640 plus 128. Oh, 2. Yeah, where did that 12 come from? Oh, I know where that 12 came from. 2. Thank you, thank you. That's my fault. 2, so it was 128. Sorry, I wrote 2 here, and all of a sudden I wrote 12. And then 12, and... All right, everyone got that? 128. Now plug in 6. I think it's going to spit out 0. Because 2 times 6 is 12. 12 minus 12 is 0. So 2 times 0 is 0. So right now, at this point, I am not able to say that this is my global max and this is my global min. I'm not allowed to say that yet because I have not checked the endpoints. The endpoints might be bigger or smaller. So now what we're going to do is step 2, evaluate the function at the endpoints. What are the endpoints? 0 and 6. So I need f of 0 and I need f of 6. Now we just happen to have already found f of 6, didn't we? It turned out that one of our critical numbers was the endpoint. It just happened to work out that way. Coincidentally, it doesn't always happen. So what happens when we do this? We already know we get 0 here, don't we? What about when we plug 0 in? 0 times 12 minus 2 times 0 squared, and that's also 0, isn't it? Yeah? Plugging into the original function. We plugged in, man, I'm just having one of those days, it appears. This should be what? 6. Why aren't you all, come on, sharpen up over there. That should have been a 6, right? 6, 6, still 0. I was actually going to put a 12 here just to mess with y'all, but I screwed it up anyway. This should have been x times 12 minus 2x squared, which is x times 0, which is, okay, so this is 0, this is correct, and this one is 0 from here. Are we all right? Fumbled that up pretty good. What's step 3? Compare your answers. So let me write down all the values I had. I had f of 2, f of 6, f of 0. Those are the only 3 that I really had, right? Those 3? Let's compare them. F of 2 gave us 128. F of 0 and f of 6 both gave us 0, which meant that the minimum value is 0 and the maximum value is 128, right? Now, this is acceptable. Books will do it this way, but I think it's actually useful at this point for you to not only understand what the maximum values and minimum values are, but to list these things out as ordered pairs, like points on the graph, because this minimum value happened at 2 different places, didn't it? And what I could do is I could write it like this. When I plug in 0 for x, it spits out 0. And when I plugged in 6 for x, it spit out 0. Right? That's a little and symbol between those. And then here, I plugged in 2 for x and got 128. So what you can see here is the y coordinates are still represented. I still have, yes, my minimum value is 0, my maximum value is 128, but this, by writing as an ordered pair, you're actually able to tell me where it happens, as opposed to just what it is. Understand? So on test, I will ask you to write these as ordered pairs. List them out as points. All right, now let's take a look geometrically at what we just did. God, how many windows do I have open here? I'll bring up good old wind plot, type in the function, which was x times 12 minus 2x quantity squared, and there we go. Wow, that's not working out too good. Okay, so what I'm going to do here is go in here. I'm going to lock my interval. Where was I looking? Between where and where? 0 and 6. And then, how do I change my view? See if this helps. There we go. That is the graph of that function on the interval 0, 6. And what we were able to determine, let me do one more thing here. I really wish we could see the x values. It's not showing my x values. But if this is 0, this is 6, right? And you can see that we have local global minimums here. We have a global maximum up here at 128, and where is it occurring? What's the x value that that's occurring at? 2. Now this is smart enough to be able to find the extremes. So it found the extreme right here, 6, 0. You see that? If I hit next extreme, goes back 0, 0. It found it. Next extreme, 2, 128. See that? Just did all the calculus we just did. It did it in a split second, right? Got it? All right. Now, this is what would be considered to be just the raw problem. You're trying to find the global max on a closed interval. Now, I'm going to give you a problem, and it's going to be in terms of a word problem. And we're going to see if we can do the same sort of thing. All right? A box with an open top is to be made from a 12-inch by 12-inch aluminum sheet. The corners will be cut out and sides folded up and welded. See if we can just get our heads around that. I haven't even stated the problem yet. Anyone have some scrap paper? This is, just have a piece of paper they can sacrifice. Bonus points, 10 points. No, I'm just kidding. There you go. All right, there you go. It was already dead. Right? I guess you're talking about the ones that are going to have to replace this. Okay. Remember what I said about the planet, right? Don't worry about it. It's all good. Okay, this is supposed to be a 12 by 12 sheet of aluminum. I know it doesn't even look like a square, but let's just act like it is. So what we're going to do is we're going to form a box with an open top. And so what we're going to do is we're going to cut the corners out like this. Right? Like that. Cut those corners out. We're going to fold the edges up. This. And we will have created a box with an open top, right? We're going to weld these edges up, right? We're going to weld them. And this will be my little box with an open top, right? Okay. So now the rest of the question. Find the dimensions of the box with maximum what? What do you think I care about here? With maximum volume. So I want to create a box where I fold these corners up. Can I get another sacrificial sheet here? Here's box A, okay? Can hear the trees screaming. Ah! Okay, so here's box B. I'm going to try a different variation of this. Bigger corner I cut out, right? Now these have to be the same size, right? When I'm cutting these corners out, all these corners have to be the same. This is fun, isn't it? This is almost like we're an activity day, craft day. All right, so I'm going to fold these up. Same sheet of paper, right? Box B. Box A. Do they have the same volume or not? Does how much I cut out of the corner affect how much it holds, or should they both hold the same? What do y'all think? Let's take a vote. Get your clickers. Never mind, no more clickers. You're just going to be, How many of you, show of hands, think that these will hold the same volume regardless of how much I cut out? Same volume? Really? Really? Okay, same volume. How many of you think that there'll be different volumes and it'll depend on how much I cut out? So everyone, okay. Usually a lot of people think it's going to be the same volume, and I have to convince you it's not. But I'm still going to convince you it's not, all right? These will not be the same volumes, all right? So what I want to know is exactly how should I cut it to get the most out. Not guess it. Tell me exactly where I should cut to get the most volume. Because there is a best solution to this. There's an optimum solution. So let me first convince you that it matters. So let's take case A just to throw it out there. I came in here with my sheet of paper, right? My 12 by 12. And let's just say I cut out 1 inch from each corner. Those are ones, okay? Cut them out. And then I fold the sides up. When I fold the sides up, pardon? What's neat? Oh, thank you. No, I can't draw. I can draw linear things. I cannot draw anything that requires trying to make it look like a real person or anything like that. Stick figure is about all I can do. Okay, so do y'all see that box? All right, what are the dimensions of this box? How wide is this side? And remember, this was a 12-inch to start, right? 12-inch here. This was 12 inches here. That was start the problem. So how wide is this? 10, because you cut 2 off from each side, didn't you? 1 inch, 1 inch. Now it's only 10 inches wide when you fold it up. So this is 10. This side's also 10, right? Because it was a square. How tall is it? 1. What's the volume of a rectangular box, or technically a parallelepiped, a 3-dimensional box called a parallelepiped? Length times base times height. So the volume will be length times width times height, base times height, however you want to say it. So the volume will be 10 times 10 times 1, which is 100 cubic inches, because it's inches and it's cubic. Its volume is measured in cubic. So 100 cubic inches if you do it that way. Is that the best we could get? Well, let's try a different case. Case B. How about we go for 3 inches this time? You want to try 3? Kind of over-exaggerating, but this one will be a little more narrow, won't it? But taller. So I give up the width, but I gain height in it. How wide is it? 6 inches, because you cut 3 off from each side, right? So you're left with the 6. Are y'all okay with that? Okay, so 6 here, 6 here. How tall is it? 3. The volume of this will be 36 times 3, yes, which is 108. 108 cubic inches. This was better, wasn't it? I got a little more out. So maybe 4 is even better. What do you think? Let's just do it mentally. What if it was 4, 4, 4, 4? How wide would each of these be? 4, 4. So you've cut out 8, so you've got 4 left over. That makes sense? So you would have something that looks like this. 4, 4, and what did I cut out? 4. What's the volume of that? 60, uh-oh, fail, right? We've pushed it too far, haven't we? We've gone too far. So we got to pull it back a little bit. So we could sit here all day long and we could try and figure out what the best solution is, or we could not care, right, and just make a freaking box. And if we need more boxes, we need more boxes, right? But if I'm manufacturing, you know, several thousands of these, right, and it's aluminum, and aluminum isn't cheap, then I want the optimum solution. I want to know how I can make these hold the most so I'm not wasting money and material. Understand? So, how can I come up with an optimum solution? How about we start out with our sheet? This isn't going to change, right? And 12 and 12. How much I cut out is a variable here, isn't it? That's a variable. I can cut out from here however much I want. Why don't we call that amount that I cut out X? Right? Let's be real rebellious here and just go for something we never even talk about, X. All right? So we're cutting X out. We're folding the edges up. That's right. How wide is it? 12 minus 2 x's, right? You started with the 12. You cut x off from each end, so it's 12 minus 2x. What about the one on this side? Same thing. Does anyone have a question on where I'm getting 12 minus 2x? That's a critical part of the problem. 12 minus 2x? We're good? How tall is it? X. What's the volume of this thing? It's 12 minus 2x times 12 minus 2x times x, isn't it? I could have written it this way. That's the problem that we just did, isn't it? Now hold on, we're not there yet, okay? I want to know, right, the maximum volume, right? I want to know what's going to happen. I actually want to know what the dimensions of the box are that give me the most volume. But that's going to mean that I need to find out when that maximum occurs, right? So here's the volume function. I want to know when it's the biggest it can be. But I need a closed interval. So x is the variable, right? X is how much we cut out. So when I was here with my 12 by 12 box, what's the least I can cut out? What's the least I could ever cut out? How about we don't cut anything out, right? And then you just have a sheet with no height to it, right? And therefore you have no volume. But you still have a smallest value that x could possibly be, which would be 0, right? So the x here could be greater than or equal to 0. Is there a maximum x I could cut out? 6. It wouldn't make sense after 6, because if I cut 6 in each direction, right, 6, 6 here, I could do 6 here, they would meet in the middle, and then I cut 6, and I have no more box, right? But that's a maximum. I'm not a max. I don't want to mix up the. That's an end. That's a greatest value I can have for x, right? I can't say 12 because then I couldn't cut all the corners out. I go too far. So halfway would be the most I could go. So that's 6. In other words, I'm on a closed interval 0 to 6. Understand? My x is between 0 and 6. I forgot to put a little less than or equal there. So I'm trying to find the maximum maximum value of this function on this closed interval, which is what we just did. The maximum value of that function. Now, I called it f of x, but we could call it v or v of x or whatever. We went through all the work, and we found out exactly that x should be what to get the maximum value? 2. If we let x be 2, we will get a maximum volume of 128 cubic inches. There's no better way to do it. That's the best way to do it. And we have the graphical support of that right here. Don't we? So what it is it's a word problem, a real world word problem that is translated into a function on a closed interval, which we apply calculus to be able to find the highest point of. Understand? It's the idea. Now, we are going to spend a significant amount of time on word problems later. Right now, today's section is just about practicing doing this part of it. Okay? Just I give you the function, give you the closed interval, you go find critical numbers and all that stuff. Later on, you can see where we'll take it, right? Those are called optimization problems, and they're, here it is. We have a lot to do before we do that. Oh, shit, no. My calculus toolbox spilled. So we have, I'll get to your question, hold on. So today is about max and min, then we do what's called mean value theorem, then we do derivatives in the shapes of graphs, then we do curve sketching, and then we do optimization. So this is the last, optimization word problems is the last section from chapter 4 that will, well, the last one before the test. Question? We're gonna move to mean value theorem. Here's the reason why we cannot continue with this right now with more word problems, because right now we can only find the max and min values of a function on a closed interval. And when it comes to real world optimization problems, if you get lucky, you have a closed interval, which we did. But a lot of the good problems in optimization problems don't have closed interval. Oh my God, I felt like I had 40 minutes left still. I have 10 minutes? Jeez, man. I guess I was just yapping too much. We did too many examples in the beginning. Okay, well, you're going to have some fun then. We are definitely going to have to come back and do more, because the derivative of this thing, right, when we did this problem, this derivative was, I hate to say easy ever in a class, but the derivative of that was easy, right? You had no problems with domains, right? This was a polynomial. The derivative was nice. Setting equals 0. The algebra was pretty simple. As you might imagine, it's not always going to be like that. So why don't you try these, and I'll be prepared to answer questions, because you'll have them when we return. Page 209. (23 through 35 odds). Okay, so for those problems, it says this in the directions. Find the critical numbers of the function. So all they want you to do is take the derivative, set it equal to 0. Also look at the derivative and see where it's undefined. So you don't have to go through and do that closed interval method where you test the endpoints and all that. Not on those. But 37 through 43 is the odds, is the full-blown find the absolute maximum and minimum values of the function on the given interval. So for that, you need to use the closed interval method. Understand the difference? The first set of problems is really like the step 1, just part of step 1 of closed interval method. Those others are the full thing. You're going to run into algebra, major algebra problems here. So be prepared for that, and especially when you get some trig functions. Enjoy. I'm shutting it down early today since I can't really get into a whole new problem at this point. Have a great day.